All right, so welcome to the recording of our tutoring session today on April 28th. We're going to go ahead and get started, and today we're talking about FRQs, how to write them, what to expect, and some things to take into consideration. So the first video we're going to watch here is an introduction to QQTs, which is qualitative quantitative translation, or vice versa, quantitative qualitative translation. Really doesn't matter. You're going back and forth from actual numbers and calculations to qualitative estimations of like greater than, less than, that kind of thing, and answering questions along the way. And then we will transition into a experimental design and how to set those up, which will be very similar to the second problem on your mock exam. All right.
Welcome to Quarter 2 AP Physics Embedded course. This is Christian and Anthony is going to do the next video for us. We just want to welcome you to the course and tell you we're super excited to do this one. This one is going to be on qualitative quantitative analysis, or QQT, and we're going to spend a good amount of time just kind of going through and making sure that our students all can do these by the time that the test comes up. The thing that we want to kind of start with here is just looking at what that QQT is. So on the AP Physics 1 at CED on page 216, it says the following examples of kinds of free response questions found on the exam. And if you've ever looked at this, you know that there is one experimental design question, there is one quantitative qualitative translation question, there is one paragraph argument short answer question, and there are two additional short answer questions. So one of the things that we want you to remember is the experimental design question is worth 12 points. The quantitative qualitative translation is also worth 12 points. And then the paragraph argument short answer question and two additional short answer questions, those are each 7 points. So we're dealing with a bigger point value question, so we want our students to do the best they can, try to get as many of the points as humanly possible. So if we look
as physically possible.
And incidentally, this is really where Unit 2 or but it goes through and it really just kind of tells us what students need to be
45. And then you round down, so it's 40 total points.
We express those key elements of data across multiple representations and domains. That's one of the science practices that you'll kind of go through. And so the skill to do that really is in that qualitative quantitative translation. And that's really just a very long true response question, and students have to go back and forth between words and math to analyze the situation. So one of these questions might ask students to work with a lot of different representations or evaluating other students' words. So you'll see like Jenny and Sue are out and they are about to fire a cannon, and then they have them go through and do things like include mathematical equations. They have to get narrative descriptions, like graphs, diagrams, data tables, all kinds of things like that. If they have been primarily exposed to just problem solving, they will struggle big time with this. So one of the things, especially for new AP physics teachers, is to wipe away all that stuff you did in college in terms of problem solving and start to realize that the conceptual understanding of both that content representations is much more important than being able to just plug and chug. So you have to watch out for that.
Which is why we talked about graphs today.
That you can get students to translate between those different representations. So looking at equations, diagrams, graphs, and written descriptions, that will really help those students prepare for QQT questions. So here's the funny thing about the CED, the course exam description. On page 43, they call the QQT a qualitative quantitative translation. That's what I'm normally used to. But on page 216, for some reason, they flip it. It's just something kind of weird and interesting, so that can blew my mind. So what's the point for students? In other words, our students have to be able to go back and forth between that quantitative or equation based on all those numbers or equations at least, and the qualitative for the words part. So this is the 2017 AP Physics 1 straight response question. We've got a disk, it runs into a rod that has a pivot on the end. They mark the center mass. They take the X position here where the disc is. They get the length as.
So I want you to think about it. What unit is this from?
This is from rotation.
Rotation. So we've got a pivot point. We've got a long lever. We've got a disc that's going to strike at some radius from that pivot point. So that's just making sure you're paying attention.
Rod, and then they go through and give you some information. So we're not going to actually do this problem. Instead, we're going to kind of look and see where qualitative and quantitative actually appear. If we look at part A, they talk about the rod being more massive than the disc, and they talk about angular speed, and they want you to figure out they want the students to figure out, to give it a whole bunch of angular speed, where should the disc hit the rod in terms of C? So
I want you to think about this. So if we're doing it, we might as well talk about this question. So if you want the most change in angular speed, what are you going to need the most of? You're going to need the most torque. And in order to get the most torque, you need the most radius. So given that point C is to the right of the pivot point, where would you want to hit the stick? Would you want it to the left of C, at C, or to the right of C? To the right of C, because that's going to give you the most radius, which would then translate to the most torque, consequently giving you, it seeing as the rod's not going to change this moment of inertia, the most angular acceleration alpha.
Really, in part A, students are just asked to determine where that disc should strike from and make that final angular velocity really high. And notice that it says briefly explain your reasoning without manipulating any equations. So this is qualitative. It does require students to write out a lot of words and explain the physics behind reasoning. So this is a good place to do the BCB/A format of writing, where we do basic physics, we cite evidence.
BC, basic physics, cite evidence.
And then we draw it together and answer the question.
Draw it together and answer the question. So you state a basic principle of physics. That would be mentioning the definition of torque and the relationship between torque and angular acceleration. Cite evidence. Well, in the problem, what would tell you, what would give you the most torque? Well, that's going to be the distance from the pivot arm. You'd cite the evidence that to the right of the pivot arm would be the furthest radius. Then you draw it together and answer the question. Based on the fact that increasing the radius of applied force increases the torque, and that the torque would then consequently cause an increase in angular acceleration, then if you apply that force to the right of C, you'll get the most torque, causing the most angular acceleration, and that would be the answer they're looking for. You don't have to write an equation for that. You're just stating basic principles of physics. And generally what you're going to do is you're going to reach for the equation that applies there and then explain it. Explain the principle behind it.
All those things at the same time. All right, so let's go to the next ones. Letter B and C, students are going to give equations, and these equations might describe the angular state of the rod after the collision. Notice that they're not the same, they're a little bit different, but the students then need to take these quantitative student answers or the equations and translate them to a qualitative reason if the equations make logical sense. So they're explaining these equations. So that's the quantitative to the qualitative reasoning. So again, they're asked to briefly explain your reasoning without writing an equation. In other words, they've got to tell, do these things make sense? In parts D and E, we've got a little bit more of the simple.
So just really quickly, let's look at those just to make sure we can kind of see what's going on here. All right, situation one is that angular speed is equal to the mass of the disk times the velocity. This is given in x direction, all right? And then over moment of inertia, okay? So what mass times velocity give you? It'll give you momentum, all right? So regardless of whether the equation is correct, does it agree with your qualitative reasoning from part A, meaning that you would put it to the right of the center of mass. And then here, you're going to see that it is moment of inertia times velocity over mass of the disk times the distance raised to the 4th power. All right. So there we've got that. And you have to think about, if I plugged numbers into this equation, would it give me what I expect? Right? So if the mass of the disk went up, would the angular speed you get out of the contact go up? That's what the first equation suggests. And then you can also then look at the second one. If I increase the distance from the pivot point, that will cause the denominator to increase here. And it would do so exponentially. So would that then translate into a greater angular speed? So this seems to fight your reasoning, right? So regardless of whether the equation is right, what you're doing is you're looking at the relationships of proportionality. That's all you're doing. So you think about the statement you made in A. Okay, I said that to the right, which means increasing D. And then you see, okay, well, B really doesn't argue with my argument. But C, it's directly opposed to what I said. So you make a statement, yes, no, and then based upon your answer in A, generally the briefly explain your reasoning, you just have to make it match what you said, even if what you said in A is wrong. Does that make sense? It has to be consistent. Yes.
So, like for the first one, isn't that moment of inertia in the denominator?
Yes.
Wouldn't that contradict? Because that would be saying that this moment of inertia radius is radius squared. That would be saying a larger radius equals like a lower moment, a large radius equals a lower angular speed is what that implies, at least as far as I understand.
Okay, so you're saying that as you increase now, the moment of inertia would be the distribution of mass on the rod, and the placement of where the disc strikes does not affect the moment of inertia of the rod. So it's independent of changing where the disc hits. Really, the only thing your argument A made is where the disc should strike. And so you're looking for this, and doesn't. So the question is, regardless of whether this equation for angular speed is correct. So it makes a statement that this is very likely incorrect. They found it on the internet. We don't know. Does it agree with your qualitative reasoning? Does it agree with you? What this does is it says, do you know what you just said in A? And if you do, can you back it up and argue against someone else's argument? And so A or B here would not argue with what you said, because no variable there would be affected by what you said. However, in C, there's a direct statement that D is not only in the denominator, which is wrong, but it's to the 4th power, which is exponentially wrong. And so you would state, based upon the fact that D's there, if I moved it to the right, my statement was increased radius gives me greater angular velocity or angular speed. And that would not be the case for C. So that's where you would hone in on. You're looking at manipulating the proportionalities and whether those proportionalities agree or disagree with what you said.
So to explain these equations, so that's the one to the quality.
Meaning, don't use an equation, use sense. Like, just think about how this matches what you said. So the point here is to take quantitative and make it qualitative. If you use an equation in your answer, you've made it quantitative to quantitative, and there's no translation happening. So it's asking you, anytime you're given an equation in a qualitative quantitative translation, you're supposed to then provide a qualitative answer with no explanation using an equation. And then vice versa, sometimes they'll give you a qualitative reasoning, and you're supposed to then use quantitative reasoning to give an answer there. Yes.
More about when it says that it does not make 50%, because it's based on, because your answer is based on what you said in the previous statement.
Right.
So when it says it's not make 50%, I'm kind of what you're trying to say.
So notice here and here are two different statements. You've got A and C, another student Deriving an equation for the post-collision angular speed of the rod makes a mistake and comes up with this. Without deriving the correct equation, how can you tell that the equation is not plausible? In other words, that it does not make physical sense. And you'd hone in on the fact that this is down here. So you wouldn't say this is the right equation and this is why it's wrong. You'd say that if this were right, then increasing the radius would thus decrease the angular speed, which does not make physical sense due to my argument today. Now, you're not referring back to A for C. B refers back to A. C here is just looking at this. You are, I thought that they were both asking you to refer back to A here, but in actuality, you're just disproving this using your reasoning. So this doesn't make physical sense because D is in the denominator and it's raised to the fourth power. Okay? Does that answer your question?
I'm just confused as to what, because you're not allowed to refer to an equation. So would you just say,
You would say that if D in the denominator, you can refer to this equation. If D is in the denominator, then that would mean that increasing the radius of impact would decrease the angular speed. And that would mean that the further you hit an object from its pivot point, the less angular speed you got in an exponential way. There should be no reason, if nothing else, you could hone in on that 4 right there.
no, like, I understand that, but how are you supposed to prove that that's correct, is what I'm trying to say. Like, you can say that, but what's supposed to be your proof as to why?
The basic physics that you stated in your first statement that did not use an equation. You can talk about torque without talking about the torque equation. You just don't write an equation and just talk about torque as a concept, which is a force times radius. And you could just talk about how increasing the radius should increase the torque, not decrease it. And if torque goes up, then angular acceleration. You're talking about principles there, not equation relatability.
In other words, they've got to do these things to make sense. In parts D and E, you've got a little bit more of the same thing going on. And so in part B, we described an event changes slightly, and students are asked to do their own quantitative analysis. So here, they are expressing their answer in terms of P, M, disk, I, X, and O, and physical constants. It's appropriate, so they're coming up with an equation. So they're manipulating equations, they're doing that, and we call that the quantitative analysis in the numbers. So don't confuse your kids by telling them, well, you're going to have to manipulate numbers. No, it's really equations for this. In part E, the described event is changed even further, and students are asked to qualitatively determine how the final angular velocity of the rod changes. And again, it does ask them to briefly explain the reason. So that is an excellent example of a 12-point QQT, whether it's qualitative, quantitative, or quantitative, qualitative translate.
So if we're looking at D here, immediately before colliding with the rod, the disk's rotational inertia about the pivot is m disk x squared. That's rotational inertia, right? Where it should be r squared, but it's the distance along that pivot arm. And its angular momentum with respect to the pivot is m v initial time v initial x, which is the direction of that initial velocity. So derive an equation from the post-collision angular speed for the post-collision angular speed. Express your answers in terms of these variables. All right, so you'd say that you'd figure out, well, how are they related? And you'd use moment of inertia, the mass of the disk, the distance. So you'd use all the things that they stated in the problem. Those are all the variables you had given there. And you would want to make sure that things are on the right side of equations. And you'd want to use all of the variables given. Then here, it's talking about it bouncing. This would be using your understanding of momentum and energy, the idea that if it bounces off, it now has gained more velocity off. It has imparted more force. So the force of the impact has gone up. And given that the force of the impact has gone up, it will be greater than it would be otherwise. All right. So you could prove that to yourself if you bounce a ball off of a bottle. When it bounces, it's going to then impart more force because the change in momentum will be greater. The time of impact will be the same. The impulse will be greater. Thus, the force is greater. And then you'd explain that. You'd explain how momentum would affect that. This is a huge problem. Like this problem uses 3 different units, and that's how QQTs generally will be. You're going to have to weave together multiple units, which is why studying the concept is so important.
So hopefully at this point you can see how the problem really requires the student to translate back and forth between that quantitative and qualitative. They're really saying the same thing over and over and over again. So when you have students do these, I know both of Starman, who does an excellent job with AP Physics too.
Yes.
One of the conspirators, is what they call it. But he's one of the co-chairs of the he does a great job of explaining this. He just says kids are going to say the same thing over and over again in different ways. So that's the nice thing.
So you're going to make a statement initially, and you're just going to continue to repetitively prove that that statement was correct. You probably want to be consistent. If it asks you to refer back to something, keep your argument consistent. If you discredit one thing, then they're both wrong. Like even if your initial argument was wrong, if the next question asks you to refer back to it, as long as your argument is consistent, you might get points for the second one, even if you miss points for the initial statement. They're looking for consistency sometimes. All right, so make sure you're consistent all the way through your argument. So the rest of it is for the AP teachers talking about what follows, because this was from the first week. So now what we're going to do is we're going to end on talking about experimental design. And this is the other 12-point question. I wanted to front end 12-point questions because those are where most of your points are going to be for your response questions. So you need to write this diagram or this mnemonic device down. D dash capital S, capital Q, U, capital A, capital R, capital E, D squared. I'll give you a second to write that down.
Did you know that flipping physics has like example FRQs like completely worked out, like look at? It's looked up
On
that
AP
one.
Central?
No, on flipping physics.
Oh,
Like,
flipping
the guy
physics.
has his own website that has he's answered all of them. Or at least on this, on this FRQ, he answered all the questions.
Is that the one that we were just looking at? 2017, number 1?
Mhm.
I did not know that. I will share that with the class tomorrow.
I
Friday.
assume he must have more if he did this one.
All right, so let's go ahead and break down with D square. You might just like remember D and then the square there if you can remember that what SQUARE stands for. So D stands for diagram. Now this document is in Canvas. It's somewhere way back in the past. Whenever I was taking this course, this is the second quarter. So this would have been second 9 weeks, probably toward the beginning of the second 9 weeks. So realistically, sometime in October. This document is there. I'll put it into the module sometime before Friday. That's got the requirement or the study materials. So you've got diagram with labels. Anytime you're being asked to set up a procedure, you want to draw the diagram for what you're setting up, because if you poorly describe the setup, the diagram could potentially carry you through. The diagram is going to allow you to refer to things, and it's going to help you keep your thoughts straight. It should not take you a super long time to draw that diagram. It literally, you can just draw a box and call it a motion detector. You don't have to draw a box with a gap under it between it and the track. You don't have to draw the scaling for a ruler. You can just draw a rectangle with some lines drawn on it really quickly and say that there's a ruler there. All right, if you label it, it doesn't have to look like the thing it's supposed to be. All right, but the diagram will definitely help you out, and the picture can be worth 1,000 words. So if you diagram it and it's right and your setup is not perfect, you might have shown something in your diagram and forgot to mention it in the setup, and they might count it. All right, this is not something that AP comes up with. This is something that AP teachers have realized is the best way to do it. And so this is like a cheat sheet essentially to guarantee that you hit all the checks that they're looking for. All right, so if you remember the not the QQT, the experimental design question that we had, now talking about the analysis, that would probably be where you start losing points. But you want to make sure that you're going to have a question like this. So you want to make sure you can follow this D squared procedure really well, just to ensure that you've got plenty of points to spare if you end up having trouble later on in the question where it starts to get in the weeds. All right, you should bank on the fact that you should get all the points for the experimental design setup. No matter what the experiment is, unless you have no idea what equipment to use, and hopefully we've done enough labs to know that generally the things you're going to be using are a motion sensor, a force sensor, a stopwatch, a mass, some kind of scale, maybe a ruler. That's pretty much it. Like literally, that's it. That's all the basic print. Like the equipment that you need will need to measure one of like 7 variables. So you'll be looking for forces, motion variables, which will be position, velocity, and acceleration, which all come from motion detectors. You could also get a length of something. You want a ruler for that. Anything that has an X in the equation. So especially when we're talking about spring energy or spring force, you want to make sure you measure distance there of compression or expansion. Mass is pretty commonly something that you're going to have in an equation. So you want to make sure you have something like a scale to measure mass. A time might be necessary. So a timer. That's about it. I mean, everything else is a derivative of those relationships. Now, of course, if you're doing something with a rotation, you're going to probably want a pulley, string, something along this line. Like you're going to need the equipment necessary to do the thing. If you are doing something with springs, you're going to need a spring. Yes.
He has a 60-page like document PDF with like just a bunch of FRQs from the past few years.
I will link that into the study material. Yes.
Do you get points taken off if you add like an extra piece of equipment that you would ever need?
As long as you set up so like for instance, if you say ruler, timer, and then motion detector, like as long as you've got the motion detector on there, and if you don't mention the ruler and timer, they shouldn't take points off. You want to just make sure you have everything you need. If you have extra, I don't think they're going to take points off unless you've got something that contradicts what you just said, which is hard to do when you're listing things to measure. But if you're saying like, I mean, you could have frivolous things, like maybe you don't need mass, but you measure the mass of something. As long as you have what you do need to measure, you should be okay. You'll just end up wasting time, like ultimately.
Okay, yeah. Because I was thinking you just put every single thing ever, like
all of the things, and just cover it. Yeah, you'd end up having to explain how you'd use it. You'd end up wasting time in that case. So the diagram is useful. Make sure you label your diagram, or else it's useless. Because most of y'all's drawing skills is in the amount of time that you'll have, not good enough. All right. The next thing we do, you should do all 3 of the next things together. SQU is one thing, and then A. So what you're going to do is you're going to describe the setup, which is briefly explain anything about the experimental setup that your diagram does not clearly convey. There's no reason to say anything in words that can be said in your diagram. So your diagram can save you time. Then say what happens to the setup. Example, the block is released from rest and then slides down the incline or something like that. So the idea here is that if you draw a block on a ramp, you must describe that the block is released down the ramp. Or if the block needs to move up the ramp, you must describe that the block is struck and pushed up the ramp, or that the spring is compressed and then released. Like you have to give the procedure. This is if you've ever done a science experiment, then you know that you're essentially here doing the scientific method. You're explaining the scientific method, where you've got a diagram, you've got your setup, which is your procedure, you've got your materials list, which is given. So you've got materials, procedure, and then you're going to talk about data analysis. So then you're going to actually experiment, you're going to collect data, you're going to analyze that data, and then you're going to make sure the data is good by repeating it and doing multiple trials. Like that is the experimental design, which is why this is called experimental design question. So the quantities are, you're going to state what quantities will be directly measured. All right. So you'll need to make a statement that any calculations will be analysis. Any calculations you do, think about all the labs we've done in class. Those all came after the data was collected. And I often told you collect all data, then do calculations. Yes, RJ.
You did say, I'm pretty sure you told me to say, you don't have to justify like things in experimental design, like why you do it the way you do. You don't have to justify it.
Right. You don't want to spend any extra time adding in jargon. All right. They are physicists. Anybody who's grading the AP test is a physics teacher. They are an AP physics teacher. So they not only have been teaching their kids this stuff, they've been doing it for probably multiple years. Most AP teachers that do reading are, 5-10 year veterans. So some of these people were there before the test changed to its current format. It's only been in the current format it's in now for 5 years. All right. It used to be A, B, and C. Now it's 1, 2, and C. And it's the curriculum changed drastically. It used to be very plug and chug heavy. Now it's very concept heavy, which kind of is good and bad. All right. You can't plug and chug your way through it. So you can't BS your way through the test. You have to really know it. All right. But you don't, if you're a good math student, then you don't get to shine where that's concerned. So it's kind of a pro con. The quantities that are being directly measured will be what you're using your setup to do. Okay, so you're using a motion detector. Just stating motion detector is not good enough because that could be position versus time, velocity versus time, or acceleration versus time. So you're going to talk about how you're going to use it and what quantities you'll be getting from that. Yes. No, that will be like what you're doing there, but it's part of the setup. So if you remember the question from the day or from yesterday, sorry, it's been a long week, then it gives you boxes. Every question you've ever seen gave you boxes. It tells you apparatus, thing to be measured. That covers the Q&A for you. They've set it up for you. And then it asks for a procedure, which is the setup. So it's all part of the same question or same part of the question. And that's why they've got it linked here. All right. Now, the AP test started structuring it that way because students were not doing well. They weren't remembering to mention quantities. They weren't remembering to mention the apparatus that they were using. And they might get a procedure, but if you don't list those things out, it's very easy to have that procedure kind of fall apart. You want to explain what you're doing in your setup, your procedure, but you don't want to over-explain it. Again, they know what you're trying to do. They know what the question is, and they've read 1,000 tests probably before they get to yours. All right. They go through tests like crazy. It's insane how many tests they have to grade per person. All right. Which is why you want to make sure you write as legibly as possible because they don't have time to spend trying to decipher your hieroglyphs. All right. They generally will give it 3 tries. They sit next to somebody. They'll give it to their neighbor. Can you read this? No. They'll take it to the table leader. The table reader can't read it. It's no credit for that part of the question. All right, they're not going to waste time trying to decipher your poor handwriting.
Yeah, I was looking at some of the sample questions for the one we just did while I was going through like looking. I could only read one of them. There's 3, and I could only like read one of them.
Physics students have some of the worst handwriting of any AP test. One of the things that I did in previous AP classes when I took them in high school is English teachers will very often have you read other people's essays from previous like online versions that they have, and they'll have you grade them 1 out of 5 to try to figure out like, is this a good essay? Is this a bad essay? Did they hit all the points? And then thinking like a reader, you then learn to write what the reader's looking for. That's the point there. And one of the times that my AP Lit teacher gave us one, he gave us an unintelligible essay on purpose, and we couldn't read it. You could read about 1 of the 8 paragraphs that were on the page, and you couldn't read the rest of it. It was just written so poorly. Of course, the photocopy didn't help. And he asked us what we scored it, and everyone unanimously was like, I couldn't read it. He's like, exactly, it's a 0. So if you're taking a lit test, be aware of that. All right. Your hand's gonna cramp. Work your hand out beforehand. All right, the last and easiest points you can possibly get. You could absolutely not understand anything about the experimental design, not know how to draw the diagram, but if you say take multiple trials of the independent variable and repeat each one 3 times for experimental uncertainty to reduce experimental uncertainty, you're guaranteed those 2 points. There are always points available for that part of the problem. All right. If you remember when those of you that were in class and I showed you the scoring guide, that was 2 whole points out of 12. That's a sixth of the points. I don't even know. It's like 20% of the possible points you could get there. Okay, it's 17%. I was close. All right. But you could get nothing else. You could have no idea and you just guaranteed yourself an extra 2 points. And then 2. Oh, that's out of 8.
Yeah, and they usually just straight up give you what the independent variable is.
Yes,
so, yeah.
very clearly. All right, so that would be an extra 2%, almost 3% on the test. All right, and the ranges, I've got my ranges in my bag, but that could be the difference. You know, just that one thing. Likely, if you're only getting 2 points on the experimental design, you're probably looking at maybe a 2 or 3 at best. If you're going to miss one of the 12-point questions, you've kind of put yourself in a really rough scenario as far as getting a higher score. You have to do really well on the 2 12-point questions to be looking at a 4 and a 5. And the other short answer questions we're going to go over very briefly. It's going to take us like 5-10 minutes at the very end of this. I wanted to make sure to hit these. So the big ideas are you draw a picture and label it well. You describe whatever could not be very clearly shown for your procedure. You're really going through procedure for the setup. Your setup here is going to be what actually happens with that diagram and anything the diagram doesn't show. Then you're going to mention the quantities and the apparatus that's going to be used to measure those quantities. They give you a table for that generally. And then you want to make sure to repeat the independent variable and state how trials are to be repeated. So for instance, in the equation that we were dealing with in the one we saw yesterday, you would be varying the amount of force that you applied to the cart in order to increase the amount of velocity that it had going into the collision. That would be how you would vary your independent variable. Yes.
But I never say reduce human error. Is it saying just don't say that alone?
That-
or don't say that at all? Because like if you said, because basically what I
That's a
did-
cop out.
No, I basically did like the example for the last one, and then I said to reduce human error. Do this to reduce human error.
You don't want to mention human error because we're all aware that we are human and thus to be human is to err. All right, especially physicists. I promise you, if an experiment does not go well, it's not because the laws of physics broke down. It's because I failed to meet their expectations. All right, because I erred as human. So really what you're looking for is all you have to do. The only statement you need is repeat each trial 3 times to reduce experimental uncertainty.
And that's not the same thing as or.
You could
Yeah, because it does say state how trials are to be repeated.
No, one of them is to repeat with differing independent.
yeah, that gives you varied data, and the other one makes sure that the data is accurate that you took as you repeat your variables. Yes,
What if you were to say in order to reduce the
that would work well. You're really just reducing error. So do 3 trials and average the trials to reduce error. You don't have to say why you're doing it. You just have to state repeat the trials. All you got to say. So if you're not sure, never say too much because you can very easily talk yourself into a hole. Right? Try to date someone and you'll find that out real quick. Sometimes less is more. All right, just like toilet paper.
Wait,
It's not true.
wait.
No, it's not true. All right, so we've got one type of question left. We've got paragraph length short answer, and we've got just regular old short answer. Regular old short answer is like they give you a problem and there might be one thing to say and it's super short. It's generally going to follow the same diagram or the same statement that we mentioned for the QQT when they ask you basic physics, cite evidence, draw it together, answer the question. That's your goal for any of the short answer questions. So the way that works, it's going to set up a problem and ask you to analyze it or give an answer. So we can look one up really quickly. Let's see. I know for a fact I can find one this way if you give me just a second.
Did they ever figure out what they're gonna do with signature taking the exam virtually and try to do it with the Chromebooks?
Oh, for the school?
Yeah.
I have not asked Fuller. I have.
I mean, I'm not, I was just curious.
Okay, so this would have been Q3.
Well, not for this class. I mean, I assume all the people who are on virtual are going to be taking the AP test virtually.
No, Rohan's the only one taking it virtually. Everybody else is coming into class. They're coming into the school.
I mean, it is logical to do so in terms of the actual test, because like I've heard the virtual test is harder.
I think he's doing it because you really can't risk being COVID.
No, I was saying that like in terms of like just the test, it's logical to do it here, but there are extenuating factors that, you know, could make that less viable for someone.
Oh, never mind. This is an electricity question. More electricity? What? Please don't be another electricity question.
Because Mr. Sellers, didn't you say it was like the test questions on virtually were harder?
They're harder, and there's also not an experimental design question
Is that
because it
true?
requires diagrams generally, and drawing it's nearly impossible.
Is that true for every AP test that the virtual test is harder?
Yes, because they don't want people to cheat, and you can't have a proctor, so they have to make it impossible to cheat on.
Even like
All
like
the
like
questions
the
you
hidden,
couldn't
like,
Google.
the history test, like world history.
Yep, they've made the questions to where you cannot Google them.
Yeah, because my sister was arguing with me about that. She's taking virtual tests for that. I said,
Perfect.
I'm pretty sure they're supposed to be harder on the virtual test. She was arguing with me about it. So
All right, so this has the answers already written, but this is a 7-point question. Notice how short it is.
yes.
Very short. It's A, B, C. All right, so let me look up 2015. I do believe that AP Central will have that if it lets me sign in. I might have to, oh no, this is when it makes me verify right here. Oh, huh?
Oh snap! Whoa.
Verification comes up at the last second. All right, so I'm gonna let that load. We're gonna need question bank, assessments. Apparently they do not have the 2015 test. Here, I can find it online. Yep, here we go. All right, so let's go ahead and look at this. I'm going to zoom out some so we can actually see. All right, so 2 blocks are connected by a string of negligible mass that passes over a massless pulley. Now we know why they say massless pulley, moment of inertia. All right, that turns with negligible friction, as shown in the figure above. Oh, here, I was like, what? So we've got mass 1, mass 2. What do you notice? They're not drawn to scale. So, but they are drawn to scale. Anytime a mass is shown as being larger, it generally means that the mass itself is greater, but the mass's disproportionality is not proportionate to their size, if that makes sense. Like if this was half the size of that, that would not be half the mass. So the mass M2 of block 2 is greater than mass M1 of block 1. The blocks are released from rest. The dots below represent the two blocks. Draw a free body diagram showing and labeling forces, not components, exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. All right, so what do you notice about what do you know about tension? It cancels it. It's an internal force that cancels itself out. All right, so you're showing generally net external forces when you're drawing free body diagrams. So if we go back to the answer here, what do we notice? Mg, Mg. All right, so you would get 1 point for sketching only one force pointing straight down from each sphere and indicating that the force is represented by force of gravity. Now, it did mention that the magnitude was important, but they did not give any additional points or take any points away for it not being. You would inevitably, if you drew the force of gravity here to be, it would only be able to be 1 length longer or 2 lengths longer. You would still get the point because you've got a straight down arrow and you'd have to label it as mg. If you labeled it as fg, it would probably still count. If you want to be safe, label the force of gravity as mg. Yes, RJ.
I need a reminder of why you don't draw tension.
That's what I was about to ask.
Yeah.
So it is an internal force that cancels itself, right? So the only force that is not resisted here is gravity. Anytime you've got a system of pulleys, tensional force is internal, and the third law pair cancels itself out essentially. So even though it's not a third law pair, it's this idea that tension here is pulling in that direction, tension there is pulling in that direction, and the tension within the rope is the same along the entire length. So it is pulling in both directions of equal magnitude and is constantly canceling itself out from one end to the other, so that now the only two things that matter are the forces of gravity, or the force of gravity acting on the two masses that are hanging off the table. It's the same idea with a modified Atwood's machine. So if you remember a modified Atwood's machine, it's the same idea, but one of the blocks is on the table, and the only thing causing the system to accelerate is gravity. The only unbalanced force is gravity because tension is an internal force that cancels itself out.
But that's only the case because of like in this specific scenario, there are 2 blocks and 2 pulleys, right? Like,
even if there was if there was another block and not another pulley. So if you just had a block sitting on the table and you were told it was a frictionless environment, then the only force causing the system to accelerate would be the force of gravity with the hanging mass, and you wouldn't consider the tension here because it cancels itself out and it would be redundant to draw it.
So you never draw tension in a free body diagram?
That's not true. Or tension can be necessary. For instance, in the free response question number 1, for the ball, the two forces were tension and tension on the left one pulling in and then gravity pulling down. So tension is necessary if you've got circular motion because at that point it's a centripetal force.
Okay, that makes sense. Only if it's circular.
But for the whole thing, you'd notice that there was no tension drawn for the whole toy because the tension canceled itself out. It's also internal to the system. You have to think about external. You're generally drawing external forces when you're drawing free body diagrams for a scenario like this.
Yeah, because that one said it only included the left sphere. And
Right.
That's why you drew tension.
Exactly. Because at that point, it wasn't internal to the left sphere. It was internal to the whole toy.
So here on the block 1 and block 2 diagrams, you're only labeling the external forces.
Yes.
But okay, that makes sense. Okay.
So it asks you to draw that in. We can see from this that that's just mg shown to go downward. So then B asks you to derive the magnitude of the acceleration of block 2. Express your answers in terms of M1, M2, and G. So you'd have to think, well, what's being balanced here? So if we look at the answer that they give, hold on. There's no graph.
Oh yeah, it just cuts off. Oh, there.
Oh, this is question 4. We've been tricked. That makes so much more sense. Okay, so this is what we're actually looking at, not the first question. I was just immediately fooled by the fact that it started with this, and I'm sorry, I just misled you all the way.
Oh, okay.
I'm so sorry. I was trying to explain why this worked, and I was like, the MG should be different links. This is bothering me immediately. So that was my fault for not noticing that. All right, so, and then when I saw that the answer had a graph, and I was like, something's wrong. Something's wrong here. This actually looks like it's going to be the exact question we were talking about with projectile motion today. A ball thrown sideways and a ball that falls straight down. So how pertinent. All right, so now let's start it over and we'll finish with this. All right, so I won't take much more of your time. Two identical spheres are released from a device at time 0 from the same height h as shown above. Sphere A has no initial velocity and falls straight down. Sphere B is given an initial horizontal velocity of magnitude v initial and travels a horizontal distance d before reaching the ground. The spheres reach the ground at the same time, even though sphere B has more distance to cover before landing. Air resistance is negligible. The dots below represent sphere A and B. Draw the free body diagram showing and labeling the forces, not components, exerted on the sphere at time t final divided by 2, so halfway through their arc. So roughly like right here at that point. So once they've been released is really what they're going for there. And they mentioned that they have identical spheres. So what do you know about mass? Well, no, like they're equal. Right, that's all you're thinking. So this now makes more sense that both magnitudes are the same and that you label the forces to be mg.
That is very easy. I hope we get one like that on
You will probably get at least one question that is this easy, likely. The one we were looking at earlier, this one right here, it looks like it is a quantitative qualitative translation problem. So, or actually it's a 7-pointer. So this is one of the short answers, but it's one of the more difficult short answers. This is the QQT. No, wait. Nope, this is experimental design. This is the QQT. Anytime you're giving a graph, that's going to be your QQT. Actually, I think we've done one just like this, just with different Ds. All right, so let me come back to this so we can finish up. Nope, went too far. So then B says on the axes below, sketch and label the graph, the horizontal component of velocity of sphere A and of sphere B as a function of time. All right, so what do you know about so sphere B goes sideways with some horizontal velocity and sphere A has 0 horizontal velocity. So we're gonna have a constant line at some positive value for B, and you'd need to label it as B, and then some 0 value for A. We can see that A is down here at 0, B is up here at some positive value. And then C, in a clear, coherent paragraph length response. So this is where the paragraph length response happens. Explain why the spheres reach the ground at the same time, even though they travel different distances, include references to your answers in part A and part B. So what this states is you would go through, you'd say, given the fact that they both have the same mass, then the same force is acting upon them to cause them to accelerate downward at the rate of g. So we see that the horizontal velocities are different, but horizontal and vertical directions are independent of each other, and the time it takes to reach the ground is dependent upon the distance they fall and the acceleration with which they fall, both of which for both masses is identical, and thus the time is going to be the same. They fall from the same height under the same gravitational influence, you're going to get the same amount of time of fall.
Wait, so why does it matter that they have the same mass when
Mass does not influence how quickly you fall.
But didn't you just mention at first?
The masses are identical. I'm just stating that the heights are identical, the masses are identical, and that means that forces are identical. Like everything is the same about both balls. And you stating that wouldn't necessarily add a point, but it would state that you know what's going on. Yes.
I read that like that ants, like for example, in really small objects fall at a slower like rate because force of gravity doesn't really affect them as much. It's like how does that work then? Like we
You're
had
lo-
an argument about like if like an ant could survive a skyscraper, like a fall from a skyscraper, and I looked it up and it said that they fall at a slower rate because the force of gravity doesn't affect them.
So doesn't it all have to do with area?
It has to do with surface area and air resistance. So it's a ratio of mass to surface area, and their mass to surface area ratio is very, very stacked toward more air resistance for their mass, and they're not going to fall as slowly because they're able to spread out. And any ant
Okay.
falling, ants don't tuck; they spread. All right, so
But since we usually ignore air resistance, that's not a factor.
exactly. So here we've got 1 point for indicating that the difference in horizontal motion does not affect vertical motion. Vertical and horizontal are independent. For indicating that both spheres start with the same vertical velocity. They start from rest. 1 point for indicating that both spheres have the same vertical acceleration, g. They're on Earth. 1 point for indicating that the falling for the same height would take the same time. They start from the same height. And then 1 point for no incorrect or irrelevant statements. If you just make it through without making a mess up, you get an extra point. They're like, good job, bud. You made it to the finish line.
I feel like that's a pointed, like, rubric point.
The short answer responses are there to try to make up points for everything else. And we are done because that's the 3 kinds of questions we've got. So I'm going to go ahead and stop my recording.